Welcome back. Today's topic is going to be on the expansion of the universe, but just as a reminder, we talked about the structure of the universe and how the smaller things formed first, and we also talked about how some things formed from the merger of other things. Here are the choices for your quick quiz. Answer those on Moodle. So, does our universe have a beginning or an end? We're getting into some big questions here in the class, and we're going to start by thinking about a universe that's not static, that expands. This is going to be coming from 26.5, and then we're going to get into chapter 29 later. So, starting in section, oops, forgot to put my pen on here, folks. Starting from section 26.5, does the universe have a beginning or end? Well, let's start with the idea that the universe is expanding. And we're going to look at the evidence for an expanding universe. There are two main observations that helps us to understand the expansion of the universe. So we know that the universe is expanding from two observations. And we're going to look at each of those in some depth, but I'll write them down here first. Okay, we know from these two observations that the universe is expanding. Observation number one, galaxies, when we look around in every direction, galaxies are moving away from us. Why would that be? That doesn't really make much sense. All the galaxies are moving away. Does that mean we're in the middle of things? We'll come back to that idea. Before I get past this, though, I have to put one or two exceptions. There are a few that are in our local group, except some galaxies in our local group. So except a few nearby galaxies in the local group. Because in the local group, we have gravity that's kind of stronger than the expansion of the universe, and it's keeping us together. It's moving Andromeda and the Milky Way on that collision course. But if we look beyond the local group, everything seems to be moving away. We'll talk more about that. That's an interesting observation. The second observation is they're not only moving away from us, but they are actually speeding away from us faster and faster. Galaxies that are farther away from us, so we look farther and farther into the universe, and galaxies that are farther away seem to be moving faster away. So galaxies that are farther away are moving away more quickly than ones that are nearby. More quickly than nearby ones. Also kind of a conundrum, right? Everybody's trying to get away from us as fast as they possibly can. If we're here at the center, imagining ourselves there, we see the close by galaxies. They're moving away. They have a little bit of speed. But if we look further out, these far away galaxies, they are booking it. So the farther away a galaxy is, the faster it's moving away from us. So let's start by asking ourselves, how do we know that these galaxies are moving away anyway? It's going to come from the Doppler effect and redshift. So we're going to take a short tour back to chapter 5 and talk about the Doppler effect, because we need to understand that in order to know that galaxies really are moving away from us. Okay, so we know galaxies are moving away because we can see it with the Doppler effect, are moving away from the Doppler effect. Not that the galaxies are moving away from the Doppler effect, but we know that they are moving because of the Doppler effect. Okay, so what is the Doppler effect? I know at some point in your schooling you have heard about this, but you may have heard about it in terms of sound. We're going to talk about it in terms of the color of light. So what happens is that the wavelength, frequency, in our case we're going to think about it in terms of color. The wavelength or color of light coming from something that is moving shifts, either to the bluer or to the redder. So the wavelength or color, and we're going to, especially when we're looking at astronomy things, we're looking at the color of absorption lines. Remember when we talked about spectrum, how stars have absorption spectrum? We see those black lines on the whole rainbow, and those lines can tell us what something is made of. Well, turns out they can also tell us if something is moving and how fast and in what direction. So we look at those lines. We know where they're supposed to be, and we look at where we actually see them, and we see those lines in the spectrum. Let me complete that idea. We see those lines in the spectrum shift. So their color depends on movement of the star, of the galaxy in this case, of the object. We're going to break this down a little bit more, but I just wanted to write that whole thing out there. So here's our picture. Let me go up to it just again a little bit. We think about it in terms of sound. Right? You've heard the analogy of a train or an ambulance. It comes towards you, you hear one pitch, high pitch. It passes you, you hear a low pitch. The sound waves are stretched out as it's moving away from you. When we translate those sounds, the low to high, or high to low, and we turn them into blue and red, into colors, and we get blue shift if it's coming towards you, high pitch, and red shift if it's moving away from you, low pitch. Okay? And I'll have a video on the Doppler effect after this one as well. So, and we'll look at the spectrum here too. So what we see is that all galaxies, except those nearby ones in the local group, all galaxies, and I'll just write that just to be clear, except the nearby, have a red shift. Those absorption lines are not where they're supposed to be. They are all shifted to longer wavelengths, redder color. So when we say they have a red shift, that means what we see, the observed wavelength or color, is different. The observed wavelength is longer, redder than we expect. Because we know that the hydrogen atom is supposed to put out certain lines or absorb certain lines. Remember, you threw those little balls at me. I caught the red one, but not the yellow one. I can absorb red, but not yellow. Well, the colors are wrong. So we look here at this diagram, and we see here's a nearby star. We know where those absorption lines are supposed to be, hydrogen or whatever the gas is. And then we look at a galaxy and everything's shifted. Not just a couple of lines, but the whole spectrum is shifted to the red. We can match up individual hydrogen lines, but we see that everything is shifted. That tells us that galaxy is moving. As a Doppler shift, it is red shifted. So, let me just write that down. redshifted. Redshift means movement away. So we see redshift absorption lines, and that means movement away. So redshifted absorption lines, get a little more space here, means movement away. Blue shift is the opposite. Alright, I'll just put that in parentheses here. Blue shift is toward. Okay, blue shift is toward. So we see all galaxies have a red shift. That tells us that galaxies are moving away from us. Observation number 1. Observation number 2 was that galaxies are not just moving away from us, but the farther they are, faster that they are moving. Well, redshift is also really, really useful because we can measure speeds. So we can measure how fast they were going, speeds, and even tell how far away things are with this Doppler shift. Okay, we can measure speeds and distances of galaxies with the Doppler shift. With the Doppler shift. Okay? And we find that the larger the redshift, okay, the more those lines have shifted. So larger the redshift, the faster and farther away the galaxy is. Faster and farther away. Okay, larger redshift means it's moving faster and it's farther away. So here's an example here. We have a nearby star. We see those absorption lines. As we moved further and further galaxies away, they show the galaxy getting smaller as you go up. The lines shift farther and farther. Lines that were blue are now green, right up here. Everything is shifted towards the red. So clarification. Doesn't mean that everything turns red. It's everything is shifted towards the red. So like I said, blue could just become darker blue, blue could become green, green could become yellow, etc. Shifted towards the red. And we see a bigger shift and faster speeds as we get farther away. I'm not going to go into detail how we measure speed, but essentially it's tied to this same kind of analysis here. So we have a couple of clicker questions, and there'll be some videos on Doppler effect too. So here's the first one. Okay, you'll see this on Moodle. Okay, so we were talking about the type of spectrum from a star. That's a little bit of a review, right? What kind of spectrum does a star put out? Absorption, emission, whatever. And then how is it shifted if it is moving away from us? Good? Okay. This one. Now, this comes from a lecture tutorial. If you're interested for extra practice, this is the lecture tutorial on Doppler shift, page 75 through 80. So you can look at that. The question for you is going to be, what would planet A see? Would it see a redshift or blue shift? Here's the space probe. It's moving this way, moving down the page. What would planet B see? Redshift or blue shift? And then think about C and D. It's in line with them, right? Right now it's directly in line. Would they see a redshift or blue shift? So look for questions like that on Moodle.